I'm Lina, a lead AI scientist from Khalifa University in Abu Dhabi. And I'm very happy to discuss with you some advancements in AI, but from a particular perspectives of telecommunications. So our research team is focusing on the telecom industry, and we have been working around the integration of large language models and telecommunication and how these models can introduce some benefits into the telecom networks and how telecom networks actually can assess the advancements of large language models particularly. We have some initial work, but which is around TelecomGPT, but I'm also interested to present around our vision for what we are looking for a future of large language models in terms of reasoning as well as multimodal models. And when it comes to multimodal, so it's not only multimodal in the sense that we're talking about visual models like images and videos, but also taking it further into more like talking about RF signals and wireless signals. And this is while it's like I'm discussing it within the context of telecom, but it can be really applicable to different engineering systems, given that all these systems share somehow the same, I would say, nature of data in terms of, I would say, wireless signals or IoT sense data and so on. And at the same time, in terms of reasoning, which I will be discussing as well, they have some common ground. So while what I will be talking about is particularly for the telecom industry, however, it can be applicable and it can be of interest to different vertical industries as well. So starting with what have been happening around AI and large language models since 2019, I think everyone has noticed this bloom in the emergence of these new large language models since 2019, 2018, and that was in line with the advancements in computing and the capabilities of supercomputers and parallel computing, which allowed us actually to implement these models and understand their capabilities and the different tasks that they can achieve. Until today, well, like here I'm presenting up to 2023, but we're still seeing more models coming every couple of weeks with different capabilities, with different model sizes. Now, these models are different in terms of their capabilities, their sizes, but the trend that we noticed from 2018 until I would say 2023 is to come up with larger models. And that was motivated by the scaling law, which basically implicates that the larger the model is, the larger your data set and the more compute you are using, the better the performance of your model. And that's why all companies and academic institute, okay, I wouldn't say academic institute, we don't have a lot of compute, but I would say the industry were oriented towards coming up with larger and larger models. And to some extent, that was really working. And the larger model that we have, the better the performance was in terms of tasks, in terms of generalizability, and so on. However, at some point, we started to realize that as well, sometimes small models can achieve similar performance under particular scenarios. And here the question started to like for us to ask is what we can improve in these models, what other things that we can work around these models other than coming up with larger models or curating larger data sets. And the question was, or I would say the answer was around different areas. So let's stop talking about having larger model and see with smaller models what we can do, or what other things that we need to improve in these models to perform different functionalities and to give us different tasks when we are talking about the different engineering systems. And here I'm talking not only in telecom, but as I mentioned, different industry or different verticals. Starting with a multimodal LLM, and as I mentioned, so we have visual models. We have models that can deal with images, models that can deal with videos. So we need more models that can deal, for example, with acoustics or sound signals. We need models that can accommodate IoT data. So currently we don't have a model that you can feed an IoT data, which is like kind of numbers, and that model will understand what these numbers are representing. Now, talking about the telecom as well, we don't have these models that can take wireless signals and somehow explain and provide some output according to this. So this is another trend that we need to study, apart from having large models, but to have like multimodal models that can take any data modality and give you any modality, and not also constrained by textual or visual models. Then we're talking about sustainable Gen AI, and here it's not only about, I would say, reducing the compute, but enhancing the hardware in a way to ensure that whatever compute we are using, we are actually fully utilizing it either for training, tuning, for inferencing, and so on. Because currently a lot of compute is wasted due to the, I would say, I don't want to say like the uncapable hardware architectures, but the less capable, and how we can find a way to enhance these hardware in order to fully utilize this compute. And then another topic, apologize the noise, I don't know, they decided to start now. But another topic that can be interest of as well for different industries and I would say applied to different engineering systems is Gen AI or LLM-based coding. In the majority of engineering systems, it's always for us is to like, I will constrain it by engineering, not all industries, but we always have, in order to automate our systems, we always have a code that need to be understood, need to be generated, need to be executed. So having large language models, or I would say large-scale Gen AI models that are capable of generating novel or emergent codes that are needed for different scenarios in the system, this is one of the important trends that need to be focused on. Now, talking about IoTs and edge devices, also being able to run these large language models and large-scale AI models on devices in our laptops, in our mobile phones, this is as well important. We know that these models consume a lot of energy, not only in terms of fine-tuning and training, but also in terms of inferencing. So just prompting the model would require a lot of compute. And then I would say we will move more around like LLMs as optimizers, but here mainly around reasoning and how these models can act as mathematical solvers. Also, in the different systems that we have, we always have some optimization problem to be formulated and to be solved. Current large language models with different testing that we have tried, they are yet not capable to formulate, to understand some problem, formulate the optimization problem, and solve it under different scenarios. And finally, large action models, which is around how we can, using all these agile LLMs, optimizers, multimodal, and coding LLMs, how we can automate our systems or have agents that can basically take the data, understand, generate a code, and then execute the code. Not to give me a code that I executed, but to have it a fully autonomous system. And all these trends actually somehow aligns with the different layers of intelligence that OpenAI has recently somehow proposed. And these different layers of intelligence are actually a way to achieve AGI, which is artificial general intelligence, which is somehow the level of human intelligence. So OpenAI claims that if we can achieve these 5 layers, then our agents can achieve AGI. And that's actually where we are going in terms of how we want to advance in AI. Now, talking more at the telecom side as an industry, and why the telecom industry will require somehow generative AI and large language models. So roughly a year ago, the ITU, which is, I would say, one of the standardization body in the telecom industry, has proposed what are the use cases and what we are expecting from future telecom networks or 6G. Since now we are in the deployment of the 5G, what we expect from 6G to achieve. And it was around 6 main pillars, including immersive communications with multisensory environments, with metaverse and so on, integrated AI and communication, and integrated sensing and communication. And these ones, I think, highly linked, like AI communication and sensing. And we'll see like in a couple of slides around that, how to have massive communication and ubiquitous connectivity. And then we have hyper reliable and low latency communication. And all these pillars are translated into KPIs as shown in the second circle here, what we will need 6G networks to provide in order to achieve these use cases. And unlike 5G, we have here more stringent requirements in terms of 6G and networks, and that's why we will need unconventional way of incorporating AI into the telecom networks. And now with the emergence of all these capabilities of large language models and generative AI, we can see that they have a lot of potential in automating telecom networks and achieving better performance in terms of future network generations. And that's why we started the work around TelecomGPT. So TelecomGPT is basically a large language models that is tailored for the telecom industry. At the first phase, we are adopting the textual and visual, the textual models. So we fine-tune our large language models on particularly telecom data, and domain-specific large language models are essential. So general purpose models are good, but if you want a model that can give you the correct answer around a particular industry that you are considering or discussing, then you need to fine-tune it on that particular data. So in our framework, we developed TelecomGPT, where we find, we first curated 3 different data sets: Open Telecom for general telecom knowledge, and then Telecom Instructs, which is more around following instructions given by humans, and then Telecom Align to align the output with the human preferences. We designed the pipeline to fine-tune a general purpose LLM into a telecom specific one. We built the 3 different models using the 3 different data sets, and then finally we established 3 different benchmarks to evaluate the performance of the telecom industry. Maybe some of you is not in the telecom industry, but currently we are facing an issue with these benchmarks because we don't have a lot of telecom LLMs or telecom specific models. And that's why we cannot say like our model is the best telecom model, because we don't have any other benchmark or particular telecom task that we can compare to. So in our performance evaluation, we compare to general purpose models. But at some point when you want to utilize these telecom oriented models, you need to make sure that you are comparing them to another, I would say, telecom benchmark, not a general purpose one, to make sure that they are achieving the tasks and the requirements that you are aiming for from your model. So here roughly for our data sets, especially for the Open Telecom, so we have gathered all information, or not all, so a lot of information around telecom, but we focused around scientific papers, books, some codes from Stack Exchange and GitHub, because we wanted to enhance the telecom coding capabilities of the model, as well as some documents from our standardization bodies, 3GPP, ETSI, ITU, IEEE, and so on. And then we fine-tuned our model to perform different tasks. So for example, for knowledge query, meaning that you ask the model around different questions around telecom, and then the model will answer you or give you an answer about that. If you have a particular task around telecom, so the model is trained as well to take a prompt and then to continue or to fill that task for you and to give you guidance how this task to be done. And of course, all of them are telecom oriented. In terms of coding and math modeling, which are 2 important points. So in terms of coding, as I mentioned, it's one of the trends to have an LLM dedicated for coding. And here we are making it particularly for the telecom industry. So the model or TelecomGPT is capable of understanding different telecom models and as well as create different telecom codes. And the same for math modeling. We have tested with a few capabilities of generating some mathematical modeling for the telecom industry. But actually, these are like still initial stages, particularly for the math modeling, because currently LLMs are not mathematical solvers, but and that's what actually we are working on. So here we just use some small data set around math modeling for the telecom, and we fine-tuned the model to be able to fill these answers. So in terms of comparing the model into the base models, so here we don't have other telecom models to compare with, but we compared with the base models. So here to show that domain-specific models outperforms base models or general purpose ones. So almost in the majority of the tasks, like multiple choice question answering, math modeling, code math modeling, coding, classifications, and so on, TelecomGPT outperformed the base model. And it was interesting to see as well that TelecomGPT exceeded the performance of GPT-4o, which relatively much larger in terms of size. But given that TelecomGPT was fine-tuned on particularly telecom data for only telecom specific tasks, our model or TelecomGPT outperformed GPT-4o. Now, what's the next step? So conversational agents basically aligns with the first layer of intelligence that OpenAI talked about. So to have more agents that understand our language and talk to us. So TelecomGPT is basically serving that first phase, which is around conversational agent. Now, when we are talking about more, I would say, reasoning agents and more multimodal agents, we need to advance into the second step to find it or to adapt this TelecomGPT to somehow to accommodate different data modality, as I discussed, not only textual and visual, but like audio, acoustics, wireless signals. If we have even like taste signals, if we have any types of senses that we are dealing with, current models are not capable of explaining these signals or these data modalities, and that's why we need to adapt these models or to develop or somehow to enhance them in order to understand and generate this data, because this data is like applicable to different systems, and it's important if we want to incorporate large language models into different systems to be for these models to be able to deal with these data modalities. And finally, as I mentioned, the ultimate goal is to have full automation. So how we can have these multimodal telecom-specific LLMs implemented in agents who can interact with each other and solve different tasks in the network. So for example, when we are talking about multimodality, as I mentioned, we are not particularly talking about images or videos, but also going beyond into, for example, some information about the 3D environment, the positions for localization, wireless signals. So for example, one of the applications, if we can have a telecom foundation model, and then we feed the wireless signal, receive wireless signal from this environment in addition to some positions or locations for the nodes that we are targeting, then we should, using this telecom foundation model, can be reconstruct the 3D environment. And this is important in imaging and wireless signals, detection, localization, and so on. Now, when we are, for example, feeding the model with wireless signals and the 3D environment, we expect to reconstruct the positions of the node that we are targeting for trajectory optimization, for localization, and so on. And then finally, for example, I'm giving the 3D environment in addition to the positions, how I can reconstruct the propagated wireless signals from this environment. And of course, in terms of telecom, this is very essential. If you can recover the wireless signal, you can perform a lot of tasks in terms of handover, beamforming, resource allocation, and so on. Of course, the optimum is to have a model that can take any of these two modalities, and then it outputs the third modality. And as I mentioned, it's not only for the wireless signals. So Ericsson, all big companies are talking about Internet of Senses, where we have somehow to incorporate the different human senses into the information that we are feeding to our model in order to make more informed decision and more, I would say, context-aware decisions. So when we're talking about semantics, smell, touch, sight, taste, sound, and so on. So all these senses, in order to, we need actually to enhance the models that we have and to accommodate all these senses, and then to perform different functionalities or tasks in the network. For example, if I'm having more around the smell, so if I can have chemical or electrical sense stimulation, if I have any haptic sensations, how I feel this into some particular large scale or large Gen AI model. And then I can do different tasks, whether it's related to radio signals, localization, generating images or videos, output some kind of voice signals, haptic sensors, and so on. Okay. So here we did a small test to somehow to see the capabilities of large language models in dealing with different senses and how we can use large language models with the Internet of Senses to come up with some applications that are useful for us. So here what we did, we implemented this at the University of Aalto in Finland. So the aim here is to use large language models to navigate a drone where the controller is not at the same place of the drone, and the person who's controlling the drone is actually not seeing exactly from the camera of the drone, because image surveillance and video surveillance is highly demanding in terms of resources. So using them at the drones is not practical always. So what we can do instead of having this continuous video and image streaming in order to for remote control of a drone. So what we did is we used actually two LLMs, one at the controller and one at the UAV. So here we are using a visual model, which basically takes an image and then generate a prompt. So kind of a description for that image, because current LLMs are capable of doing this. Either you give a prompt in terms of text, and then you receive an image for that, as we can see from ChatGPT, or you can give an image and then ask the model to explain to you what's happening around that image. So this is what we did. So we asked the model to take just one figure and the image, and then generate for us the prompt for that image or the textual description, and then we send only, instead of keep sending images, we send only text. And we all know, like, the resources that's needed to send textual data is much less than the resources needed to send videos and images. And so at the controller side, the received prompt or textual data will be received, and then using another LLM, the textual data will be converted into an image. So here, what's the output that we got? So the first one is the real image, and then the second one, the one that is recovered at the controller side. So we can see here, we don't have a lot of details in the reconstructed one. It's not like a high resolution or high fidelity one, but at least we have the main elements and the main factors that we need to navigate a drone. So I don't need to know, for example, the deep details for that particular application, deep details of a tree, or deep details what's going on in the snow here. I need to know the main elements that I need to know in order to navigate the drone. And actually, it was, like, in terms of performance, very successful. The only constraint here, when we are talking about latency, because in order to generate the text and then send the text and regenerate the image, at the moment, this generation, the inference of this one still takes a long time. So when you are talking about navigating a drone, you need somehow faster performance in terms of latency. But in terms of concept, how we can utilize large language models for such applications, it was a successful one. And one of the things that might solve this one is how we can implement large language models actually closer to the edge. So in terms of latency, that it will be improved. Now, I think that's the last one, which I will talk about. So here I'm talking around the third element around reasoning and around math modeling. So how we can, as I mentioned, current large language models are not capable of formulating or solving optimization problems. And at the other hand, conventional optimization problems that we have in engineering systems are very constrained by predefined constraints and elements. So we cannot impose as users any constraints to our system in order to optimize in a different way. So for example, even if we have like smart, I would say AC systems which adapt to some temperature, but still there are predefined constraints that it has to follow. Now, what if we are now considering more user-centric approaches and adaptive optimization to deal with our surroundings? So for example, I don't want my phone to charge normally when I'm, for example, sleeping at night. I want to make sure that I'm minimizing the cost. So I want my phone to charge the maximum when the electricity cost during the night is the lowest. Or for example, I have an EV car, and then I want to charge this car while maintaining the battery lifetime. So I want to instruct my LLM to somehow implement my car charging in a way that it keeps the somehow, let's say it has two constraints, like I want to reduce the cost, but at the same time, I don't want to have a lot of fluctuations. So yes, try to charge when the cost is low, but try also not to fluctuate a lot. So we implemented this system where you can talk actually to the optimizer in your system using natural language. So for example, here, charge my EV for tomorrow at 6 a.m. while managing its battery lifetime. The second one for a phone, for example, adapt your transmit power to minimize electromagnetic exposure while, for example, I'm sleeping, but ensure to guarantee that my messages always go through, and so on. So this applies to different systems around us where we can interact with in order to somehow put our constraints or our preferences into how they are operating. And for that, we developed 3 LLM-based agents. So the first agent basically takes a voice request from the human, and from that voice request, it identifies what is the optimization problem class, and it converts this class into the second agent, which is the parser. Now, the parser is the most important one because it takes what is the class of this optimization problem. It also takes the voice request and some knowledge base in order to extract all the parameters that are needed to formulate this optimization problem from the human voice request. And then it passes all this information into the third agent, which is basically the solver agent, which is somehow based on the class of that optimization problem. It finds, through a bank of some solvers, it finds the optimum solver for that particular problem and then solve that problem. We applied this to AV charging. So here, for example, you can see based on the request that we wanted, this is the power and this is the time that we have. And based on the instructions we are giving, it somehow change the power level. So here I will stop my talk. All our activities around TelecomGPT is basically under our large AI models and telecom emerging technology initiatives. We are conducting a lot of projects and initiatives, and feel free to check what we are doing around these topics, and or to contact me if you have any questions around it. And thank you.